So in these types of questions, we begin to look at equilibrium from a different perspective. Now we look at the concentrations of the reactants and the products at the beginning of the reaction. In the past, we looked at those concentrations when the system had gotten to equilibrium, so after equilibrium was reached. Now we're looking at it at the initial conditions. The method that we have to use changes slightly, but we will deal with it in almost the exact same way. So what we have carbon monoxide plus water yields hydrogen gas and CO2. What we know is that the equilibrium constant KEQ is 8.3. We also know the starting concentrations. 0.20 molar of carbon monoxide, 0.20 molar of H2O. And the question is asking us to find the amount of each substance present after we reach equilibrium. So to do that, since we know the concentrations at the start, and that is key here, at the start, we need to make what's called an ice chart. And the ice chart deals with all the concentrations of all the reactant participants at initial, I, the change in concentration, C, and what they reach at equilibrium. So to do that, we need to make a column for each of the compounds. And we need to know information that is initial. We need to know the change. And we need to know the concentrations at equilibrium. So at the start, a concentration of CO and of H2O are both 0.20 molar. And we also actually know the concentrations of H2 and CO2, even though they're not directly given in the question. This is the beginning of the reaction before any of it has progressed, so the concentrations of H2 and CO2 are both 0. The change in concentration, well, the concentrations of CO and H2O will decrease because they will get used up. We don't know exactly how much, so we can call that X. But maybe not just X. We need to go back and look at the chemical equation and look at the molar ratios between the substances. We need to look at the coefficients in front of each of those substances. Now, these are all ones in this case, which makes life much easier. The concentrations of CO and of H2O will both change by X, since they're a 1-to-1 mole ratio in the chemical equation. They'll actually change by negative X, since they are decreasing. Likewise, using molar ratios, we can also find the change in concentrations of H2 and CO2. Since everything is 1-to-1, H2 will increase in concentration by X as well, and so will CO2. To find the equilibrium concentrations, we just do a little bit of math. It's the initial minus the change, so 0.20 minus X will be the equilibrium concentration of carbon monoxide. Same thing for H2O. H2, we started with 0 and we added X. Its concentration at equilibrium will be X, and CO2 will also be X. It's these equilibrium concentrations that will matter in the KEQ equation. Because remember, KEQ takes into account the concentrations at equilibrium, not at the beginning or the middle of a chemical reaction. So now that we have these equilibrium concentrations, we can go and we can create the KEQ equation. Remember that it's products over reactants. So KEQ equals concentration of H2 times concentration of CO2 divided by concentration of CO times concentration of H2O. Filling in what we know, KEQ 8.3. Concentrations of H2 and CO2 are both X, so we have X times X on top. Concentrations of CO and H2O are both 0.20 minus X. And these are brackets here. And at this point we have just a simple math exercise. Now, instinct might be to put a 1 under the 8.3 and cross multiply. That will work. However, it's going to make the calculations a little bit difficult. So we're going to treat this in a little bit of a different manner, and we're actually going to deal with simplifying the right side first. If we look at the top, we have x times x, which we could just write as x squared. On the bottom, we have 0.20 minus x multiplied by itself, which we can write as 0.20 minus x squared. Now, on the right side, by writing it this way, we've actually made it easier to simplify this. We have two quantities that are squared. We can actually just write that as the whole fraction squared, like so. At this point on the right, we have one bracket that's squared, so we can easily get rid of the square root, by taking the square root of both sides. Cancels off the squared. Taking the square root of 8.3, we would get 2.88, and that would equal x over 0.20 minus x. Now, if you're wondering why we did it this way, if we hadn't have done that, we would have been dealing with x squareds. And dealing with x squareds in a calculation means we would have to either factor or use the quadratic formula to solve, which complicates things, doesn't make it impossible, but makes it more difficult than it needs to be. By eliminating the squareds and getting down to just straight x's, we can go back and use some grade 8, grade 9 level math and solve this equation much more easily. At this point, the best option is to cross multiply, so we stick a 1 under the 2.88. One times x would be x. 2.88 times 0.20 minus x. We can write out like that. We will need to distribute that 2.88 into the bracket in order to solve this. So we have x equals 0.576 minus 2.88x. Take the 2.88x to the left, add it to the x that's there, we get 3.88x equals 0.576. Divide both sides by 3.88, rounding to sig figs, we would get that x equals 0.15 moles per liter. this is not the final answer. This is the change in concentration of each substance. So to find the equilibrium concentration, we just need to take the initials, combine the changes with it, and we will have the equilibrium concentration. So, concentration of carbon monoxide at equilibrium was 0.20 minus x, so 0.20 minus 0.15 would equal 0.05 moles per liter. Same exact method for the concentration of H2O. Its equilibrium concentration was 0.20 minus x, 0.20 minus 0.15, so 0.05 moles per liter as well. Concentration of H2 at equilibrium was just x, so just 0.15 moles per liter. As was the concentration of CO2, it was just x, so just 0.15 moles per liter.